Okay, well, welcome everybody. Let's go ahead and get started. It is a great pleasure to introduce Matt Hauer, who's going to be speaking today. I've been following Matt's career with a lot of interest. He is currently an assistant professor in the Department of Sociology at Florida State University. And he was awarded a PhD actually in geography in 2016 from the University of Georgia, where he worked on ripple effect, how sea level rise induced migration will reshape the US population landscape. And, that's a topic that I find incredibly interesting. Matt's had a range of different experiences, which I think have contributed to his very creative and it's a creative research agenda, and the way that research agenda spans, a lot of the different areas of geography and sociology. So he was formerly with the Census Bureau for a while, which I hadn't actually realized. And from 2011 to 2018, he ran the Applied Demography Program at the Carl Vinson Institute of Government for the University of Georgia. So one of the things that I've always found really interesting about his work is that he has a nice sense of what's important for sort of policy and applied work, as well as what's really interesting from both a sociological and a geographic sense. So, just looking over papers he's produced recently, I found 3 that I want to read immediately. I mean, he's been working on the built environment in Peru, in Puerto Rico, inaction on climate change and European life expectancy, and also evacuees and migrants and their patterns of migration after the Great Japan earthquake and tsunami. So these are all just in the past year or so. So he really has had this incredibly both productive and diverse set of research topics that he has explored. And he's going to be presenting new work today, Causal Inference in Population Trends, Searching for Demographic Anomalies in Big Data. So let me turn it over to Matt. Thank you so much for participating.
Thanks for having me. Yeah, actually, I worked at the Census Bureau, both in headquarters and in field. So I'm one of the very rare people that actually has field experience and headquarters experience. So this is new work. It's not on the environment necessarily. It's not necessarily on migration either, which is where a lot of my research is. It's not on population projections, which is another area that I'm very active in terms of research. Instead, it's really wedding together 3 different concepts. And so this is some work that I've been working on for a few years with Stephanie Bohan at University of Tennessee, Knoxville, UT Knoxville. And the key thing here that I'll be talking about is the sort of the uncovering of anomalies in the data that we have. And we have a lot of data in demography. It's one of the great things about the field and about the discipline is just the wealth of data that we've had for so long. So anomalies are cool. I think they're really fascinating. They've been in the news relatively recently. Perhaps people remember this kind of thing, right? An anomaly in the desert, a wild monolith in Utah that was in the headlines. This is from the New York Times just a couple months ago about this anomalous a monolith, right? This metal anomalith that was found in the desert. And then a few more popped up elsewhere, and people weren't sure where they came from. They were like, don't visit them. And one, I think, popped up in Germany. Maybe this was some kind of weird viral marketing campaign and so on. But I'm not going to be talking about this kind of anomaly at all. I'm going to be talking about statistical anomalies in the data that we use. And there's 3 main concepts in this paper that I kind of want to talk about before we actually get into it. This paper is about causal inference, it's about big data, and it's about abductive reasoning, which might be a bit more foreign. So causal inference is really simple, right? It's how we uncover the underlying mechanisms behind what we study. We want to know not just associations, but we want to know the driving forces behind them. And it's super easy on like the highest possible level. You just have 2 different effects, one where the treatment is applied and one where there is no treatment, essentially, or if you have some sort of control that's applied, right? So y1 minus y0, and the difference between these 2 generally gives us the causal effect. And traditionally, this is done using RCTs, randomized controlled trials, and it's also traditionally done through natural experiments. So, right, if you randomize your experiment and you give the treatment to one group and you don't give it to the other, we can then ideally make some sort of claim about the causation in whatever the thing is that we're studying. Unfortunately, for many of us, RCTs are incredibly expensive, and it precludes the use of actually deploying them in any type of our research. This was a tweet that kind of went viral about a year ago, that somebody was a grad student and they did a study for less than $100,000 while they were grad students. And, most of the cost was on purchasing beds, bed nets. It's still expensive, but is a fraction of what is often spent on evaluations after the fact. So conducting an RCT as a graduate student for about 100 grand. And as you can imagine, the responses to this tweet were not so kind. People from less wealthier universities really chimed in pretty heavily. The total cost of my dissertation research was $21,000. I got 9 different grants to do that. $100,000 to do my study would have been impossible. And I love this comment right below that, which is, I won a $5,000 travel grant for field work, and that was quite the treat. So RCTs can be prohibitively expensive for most people. I'm really interested in doing work on the cheap for the most part. And so RCTs oftentimes are going to be priced out for what I want to do. And in the real world, sometimes the implementation of an RCT can be completely impossible for ethical reasons or otherwise. How in the world might we implement a randomized controlled trial for country level austerity measures, for instance, right? We're going to give some countries and make them give them an austere policy and other ones a non-austere policy. It's just not possible to do. So even though this is a typical way of going about causal inference, it's not always applicable everywhere, or it might be prohibitively expensive. Natural experiments are a great alternative. It's a lot cheaper. Generally, somebody's already collected the data for you, and you can do this after the fact, but the barrier to entry is much lower. But you have to have expert knowledge of a situation in order to actually generally deploy a natural experiment. And I've deployed natural experiments in my own work in the past. I find them very, very easy to work inside. And demographers use this quite a bit. This is an active area in demography as opposed to necessarily RCTs. This is Stuart Geidel-Baston's paper in PLOS One from a few years ago that was looking at the effect of the one-child policy in China on fertility outcomes. And so the black line is the true TFR essentially. And then the blue line is the TFR without the triple L policies of 1973, what is it, the less, longer, and fewer, right? Or the later, longer, fewer. And then as well, the TFR in 1973 with the triple L policies, but without the one-child policy in 1979. And so the difference that Stewart was finding is that the triple L policies actually were the thing that reduced fertility more than the one-child policy. And that difference between those lines is essentially the causal effect for a given policy. This type of approach is when I started working on this paper, wasn't necessarily inside the mainstream, this kind of way of doing things. But with COVID-19, this is pretty much everywhere. It's how everyone does excess mortality, right? We have some sort of counterfactual of what the world would have been like had something not occurred. In this case, right, this is French mortality from a paper in Nature Medicine. And so you can see the effect of COVID and what it might have been had there not actually been some sort of not been a pandemic, right? That's the blue. It's mortality in the absence of COVID-19. These are great. Here's a famous one for this type of natural experiment that I really like a lot. It sets up the framing for the reasoning. Is a paper from a few years ago by Inev and colleagues, which estimated the effect of auction starting prices on the outcome. So does the starting price of an outcome actually drive the final sale price of that item and the probability of sale? And they had this amazing natural experiment. They were so lucky. It's what makes this paper so cool. They found 31 eBay listings for the exact same golf club by the exact same seller, where the only thing that differed was literally the starting price of the auction, of the eBay listing. So they were able to generate a causal effect out of this using just real basic causal inference techniques through essentially deductive reasoning, which brings me to the way I'm going to bridge abductive reasoning in here. Almost all of causal inference, whether you're using a randomized controlled trial or you're using a natural experiment, follows some form of deductive reasoning. You start with a theory, you make a hypothesis about it, you observe that phenomena, and then after your results, you can either confirm whether or not your theory was actually correct. I mean, this is how we're largely taught the scientific method. So for Einev and al., I can't remember their exact theory that they started with, but they do have a great hypothesis that the starting price impacts the final sales price of an item. They make an observation using eBay sellers and their listings, and then they in fact confirm that the higher the starting price is, the higher the final sale price happens to be. So this is science, right? This is deductive reasoning, and it has a really long history. In demography, we've got history like this as well. John Snow and the cholera outbreak of 1854. All right, he had a theory that it was going to be waterborne. He deduced that a bad water pump was responsible. He turned it off, and thus, right, we have the birth of modern public health and modern epidemiology. So this is really common, right? Everyone sort of has this hypothesis, observation, confirmation kind of thing. We also have, aside from deductive reasoning, we have inductive reasoning, which is directionally opposite to deductive reasoning. In this case, instead of starting with a theory, we start with an observation. We make a theory or hypothesis out of it, and then we confirm this. And I've got up here mortality. Right, the deaths per 100,000 people in the US. This is a very famous example of inductive reasoning in demography, where you can see the different mortality rates for different race groups. And curiously, one race group is lower than what we would expect. So 1986, we have an observation that gets published that US Hispanic mortality is better than expected, given the socioeconomic status of Latinos in the United States. And this observation, right, what's causing this spurred a whole bunch of theories and hypotheses, the salmon bias and healthy migrants, or maybe it's acculturation, to try and explain this observation. And we end up with confirmation of all three of these in some form or another, as well as lack of confirmation, right, where we disprove whether or not any of these theories actually work. And this is one of the problems with inductive reasoning in this manner, is that generally you're limited to either proving or disproving a theory or hypothesis, right? You either have support or you don't have support. That's the whole point of a testable hypothesis. So a third way, which is less used in the sciences, is abductive reasoning. Sometimes people will get these confused with inductive reasoning, but they're not quite the same. And essentially you're inferring a cause from an effect, and it allows you to move between deduction and induction when you're looking through some sort of abductive reason. It finds a pattern, suggests a hypothesis. Deduction then helps you refine and build a testable hypothesis, and induction helps provide the empirical support for whether or not and whatever you're observing in the world. There's a famous example of abductive reasoning in general science. And it was in 1846. There's an observation that Uranus's orbit, it deviated from its predicted orbit, and astronomers at the time didn't know why. They made a hypothesis that another body is interfering with its orbit. And then, of course, they discover it, right? The eighth planet, Neptune, is then discovered. And so we have a change in the way our understanding of the world works. This is still going on, this type of abductive reasoning, this notion of an observation and then an explanation from it in the physical sciences pretty considerably. This was from earlier in 2020. There was an anomaly detection at LIGO, the gravitational wave detection laboratory, where they found this sort of anomaly in their data in the area of the sky near Betelgeuse. And so was this going to be a new gravitational wave candidate? What was actually driving this gravitational wave that they discovered? Was it a glitch? Was it not a glitch? And so you got these really great astronomers, saying, oh, I know it's nothing, but they detected this near Betelgeuse. So I'm tying my shoes and going outside. Listen, it's nothing. I'm sure Betelgeuse is not being blown up into a supernova. Grabbing the binoculars, it's nothing, right? It's really not that big of a deal. Throwing on a sweatshirt to stay up all night, no, it's nothing. There's really great ones with this. It's not blowing up, right? So Betelgeuse isn't blowing up. It's outside the localized region. It might not be real. They didn't detect any neutrinos, right? So they're working through the different reasons using logic to determine whether or not a Betelgeuse actually blew up as a supernova or not, going back and forth between induction and deduction. And that's what I'm going to do in this paper, is use abductive reasoning in a very specific demographic environment. Now, in a data-rich environment, which is what I would classify demography as squarely within, abductive reasoning is really easy to apply for finding all sorts of different effects and then inferring what those effects might be, what have caused them after the fact, ex post. So we can do all of this now really easy because of supercomputing advances, because we have so much more data that is continuously coming online that allows for this. So I think that demographic data is an ideal big data environment for deploying causal inference techniques to try and infer the effect from a cause with abductive reasoning, where we don't actually need to know necessarily expert knowledge about a situation to deploy it. And I'll show exactly what I mean as I move through this talk. So that's what we do. We combine causal inference techniques, abductive reasoning, and then very large demographic data sets on both fertility and mortality in the US to try and identify or search for anomalous demographic behavior. Essentially, what are the baby booms and busts and the mortality spikes and dips that occurred in the United States over the last 20 years, because that's the data that we have. What are they? Where were they at? And then what might have caused some of these? Are some of the effects that we find that happened in the US over the last 20 years, are they actually detectable? So we're going to identify effects, changes, underlying changes in demography without any knowledge of the cause, right? So this is a very different realm of logic and hypothesis testing in science than most of us are used to. But it allows us to really discover what I think are really exciting things and help us explain social phenomena in a way that we couldn't do it before. So to do this, we use a relatively old algorithm. This is a time series outlier algorithm from the early 90s from Chen and Liu. And this is implemented in R through a single package called TS outliers. And now Rob Hidman and his forecast package uses this natively as well, this exact algorithm. And I believe there's one in one of the Epistat softwares uses Chen and Liu's algorithm. It's really simple. If you have a time series, the algorithm first fits an ARIMA model to the time series. And then it checks the residuals on the time series for each time point to look for their significance and identify potential outliers. If any of the outliers are above a critical value, what Chen and Liu suggests is a t-score of 3.5, then that is removed. The ARIMA model is refit with that removed, and then this process iterates again. There's a new ARIMA model that is fit with the anomalies pulled out, checked again for the residuals, and so on. And this is iterated until no additional anomalies are detected. And there's a couple of minor additional things about, like, well, what happens if you detect multiple outliers in a time period? What happens if there's two or periods or more, or there are different types of anomalies that are detected, because there are different types of anomalies. But essentially, that's the way it works, is we fit a time series, and we fit an ARIMA, we check the residuals, remove them, refit it with those removed, and continue and iterate. We identify three types of anomalies. There's additive anomalies, or in this literature, they're described as outliers. There's level shifts, where the change actually propagates into a new level, and a temporary change. So an additive outlier is really simple. The time series increases or decreases over a single period. Using sort of the same way of describing it in demography, this might be like a mortality event, right? One thing in one time period. If we're looking at a year, it might be a year. If we're looking at a month, it might be a month, but it only affects that month. And so we take it out and refit the series. A level shift is where something completely changes. Maybe there's a new policy that's put into place that prevents mortality, or in the case of Geidel Bastian's paper in PLOS One, this would be like a policy change that changes the level of fertility or mortality permanently. And a temporary change is one where it has this sort of lingering effect over time, over multiple time periods. Chen and Liu suggest a t-score of 3.5, as this minimizes the possibility of a type 1 or a false positive outlier. Though this could be, you could essentially set this as any value, especially when you're looking for like extreme outliers. I've used this exact algorithm for other purposes outside of strictly demography and more of a data science realm, in which case we needed to use a t-score of 10 to really identify the extreme anomalies, and they can pop up. So I want to walk through a quick example of how this algorithm might work. What you're looking at here is the exchange rate between the euro and the Swiss franc in late 2014, early 2015. And the central Swiss bank had pegged the exchange rate at exactly 1.2. So they always traded at the exact same value, right? They always traded at 1.2 euros per Swiss franc. So if you were to think about the continuation of this time series, right? You don't know anything else about what's going to happen in the future. You would probably pretty strongly guess that this exchange rate is going to continue on at 1.2, right? I mean, the policy is designed that way to be pegged at a given value. But on January 15th, 2015, the Swiss bank removed the peg, allowing the two currencies to trade completely freely, right? So we have a policy implementation that occurs on January 15th. And so the exchange rate changes dramatically, very dramatically, immediately afterwards. And when you run the time series, when you run this in the TS outliers time series, it detects this anomaly right here. This is our observed data Y. And our counterfactual, what the time series would have been had there not actually been a change in the peg, right? Had they actually kept it in place. This would have been our counterfactual with the anomaly removed. And this is an extremely strong level shift. The t-score for this is 144. So this is not some sort of spurious change in the exchange rate. We know that this is literally because they changed the peg. But if you had not known this and you were just going through Swiss or going through exchange rates for currencies, you'd find this and pop it up and go, what was driving this? You look and you'd say, oh, well, it's a change in the currency peg. We did a robustness check as well to double check and see what our false positive and false negative rates were. We ran 2 simulations to determine the type 1 and type 2 errors, the false positive and false negative error rates. We simulated 1,000 white noise time series. So they're just white noise. It had 180 time steps in it because that's the length of our actual time series. And we don't introduce any anomalies. So if we detect an anomalies in these time series, they should be considered false positives because they're not real anomalies. This is white noise time series, right? They're just random. It's entirely random. We detected 208 anomalies and 180,000 candidate time steps, which gives us a false positive error rate of 0.11%, which is pretty good, 0.12%, which is I would say is very good. What we're looking for. We also then simulated another 1,000 white noise time series again, same exact length, but we introduced a single anomaly of the same magnitude at the same time point in every time series. So here we're purposefully injecting an anomaly into the time series. So if we can't detect this time series, this anomaly, it would be considered a false negative, right? A type 2 error rate. We detected 817 of these out of the 1,000 candidate time series, giving us a false negative error rate of 18.3%. And so this translates into a statistical power of 81.7%, which is pretty good. So we feel pretty good about this approach, about using a t-score of 3.5 to sift through all of these time series. So we searched for demographic anomalies using monthly fertility and mortality data out of CDC Wonder. We have for fertility 2003 to 2017. For mortality, we have 1999 to 2016. So we're looking at 180 and 228 time steps. We're looking through all 50 states and DC. So this gives us a total of 20,808 state months worth of data. And we did this for everywhere. I'm not going to show all of the results for everything. I want to show the ones that I want to show three different sets of results. One's for fertility, where we have a plausible explanation. One's for mortality, where we have a plausible explanation. And then ones that are interesting that we don't have a plausible explanation for. So I think this helps show the kind of a proof of concept, again, that we're detecting known anomalies in these that should be explainable. So I'm going to start with fertility. I'm going to start with Louisiana. All of our results will look like this. They follow the same general pattern. The top series is the original and the adjusted time series. So Y and Y hat. The original is going to be in gray and the counterfactual is in blue. Where you only see blue and no gray on top of it, that's because there's no anomalies there. So we detect two anomalies in Louisiana: annual number of births, or monthly number of births, in August of 2005 and in October of 2005, right here. This is the true value versus what the counterfactual should have been, essentially, for the time series. And these are significant reductions in birth. These t-stats are not exactly small. We're looking at 6 in August, and we're looking at 5 in October of 2005. Now, if you're familiar with the 2000s, a major event happened in Louisiana in August of 2005. It got hit by a Category 5 hurricane. Hurricane Katrina hit in this exact time period right here. It hit August of 2005. And we estimate that there were 4,400 fewer births that occurred in Louisiana than would have been had there not actually been a Category 5 hurricane that hits Louisiana. These are missing births, essentially, in the state. Presumably, these women who had these children were not in Louisiana when they had their kids. They were elsewhere within the United States. And Jenna Nobles has some great work showing the missing births after Hurricane Katrina. And this is it. We're finding that. We didn't program a hurricane into this model. It's not ever implemented in. It only has one data input, which is the time series of births. And so we find that, we detect that, about 4,400 fewer births in Hurricane Katrina. So we find a major effect already and what we think is going to be a cause. Here's a second one for fertility as well. This is Connecticut fertility rates as well. And this has a level shift that occurs beginning in August of 2009. We're looking at a t-score of almost 4. It's 3.7. And this is a very significant decline. It's about almost 300 fewer births in Connecticut every month over the next 10 years, or about 28,000 fewer births that occurred in Connecticut beginning in August of 2009. Now, this is a really curious one. It took us a little bit to try and figure out what might be going on here. But we think that it's connected to the Great Recession. The largest single day loss of the Dow Jones occurred 11 months before the level shift change. So we believe that this is related to the stock market crash in September of 2008 and the ultimate fertility behaviors that occurred after people began to change their behavior. Connecticut has a large number of stockbrokers who generally commute into New York, and we think that these two are related, but we don't really know. We're detecting an effect, but we don't necessarily know the true cause behind it. Here's some interesting mortality ones. This is New Hampshire, and we detect 2 level shift anomalies beginning in April of 2010 and November of 2014. Both of these are significant, even larger in 2014, where we've got a t-statistic of over 6. And so this was curious, meaning that mortality is much higher in New Hampshire beginning in 2010 than we would have expected when we removed that data point. In fact, there's 8,000 more deaths than expected since early 2010 in New Hampshire. And we reasoned back and forth about what might be behind such a very large rise in mortality in New Hampshire. And we think it's related to the opioid crisis. New Hampshire has the second largest or the second highest opioid related mortality rate in the United States. And we believe, and it coincides directly in this exact time period. So we believe that this is related to the opioid crisis. We're finding it right here. We're detecting it right here in the data series. And we're not programming this in. This is a universal algorithm. The next one's a little bit more complicated. This is New York. And we detect 7 anomalies in New York. And I want to highlight a few of them. This is September the 11th. This is one of the main anomalies that we detect. This t-score is 6.3, so almost 6.4, so it's very, very significant. It's an additive anomaly, meaning that it is only present in a single time series, and we detect 1,600 more deaths, or we estimate 1,600 more deaths in New York than we would have expected. Now, 3,000 people died on September the 11th, but we also had less traffic and so on. So this is essentially what we believe is the net effect of September the 11th in New York. There's also very curious level shift that occurs in February of 2004 that's very significant, where we've got a t-score of 5.5, which translates into 7% fewer deaths in mortality, or 144,000 fewer deaths than we expected. But we don't know why. This comes very close to legislation. This is 12 months after legislation is implemented in New York, dealing with, I believe, the soft drink limitations that went into effect. So this could be a direct policy change that occurred in New York because of changes in soft drink usage, or outdoor smoking was another one that was related in this time period. But I don't have a direct, I don't know why we would detect such a large effect. Now, sometimes we end up with odd numbers. This is an example of one. This is fertility in Hawaii, the number of births. And you can very clearly see this one very, very strong fertility anomaly in one single month. It's an additive anomaly in Hawaii in May of 2014. In that month, May of 2014, Hawaii had 15% more births than we would have expected to occur for a t-score of 5, right? So this is very large. And this, on top of that, is the second highest monthly births in the entire time series. Now, this could be a statistical anomaly, like literally a statistical anomaly. This is an artifact of something inside the data series. If so, if this is actually just true sort of noise in it, or it's an error in maybe a keystroke error for a clerk somewhere, this is an uncorrected error in the time series. Or on top of that, we don't really know why this is occurring. I don't know. I think I lean toward this one as being one of the true anomalous ones. Maybe this really is a false positive that we're detecting here. And lastly, I'll use Ohio as well. Again, this one has countervailing factors as well. Some of them are large, some of them are not. The important one, though, here is the one in May of 2014, where we detect 40,000 fewer deaths in Ohio, or 1,100 fewer a month. And this is the single largest level shift among all states. And we don't know why. We don't know why mortality in Ohio began to drop so much beginning in the middle of 2014. We just don't know. And we ran these for every single fertility and every single mortality time series in the United States. Some of the anomalies I don't think are as interesting. As you can see, I'm only highlighting one here in Ohio. It happens to be a large one, but it's really curious that we find this. In total, we identified 22 fertility anomalies and 156 mortality anomalies. And so the fertility anomalies tended toward baby busts, where we totaled about 200,000 fewer births than we expected in the birth series. The mortality anomalies tended to go the opposite way, but they totaled 48,000 more deaths than expected. So we're looking at, on the grand scheme of things for the whole US, very small ultimate changes. But there were more countervailing mortality estimates, so some were higher, some were lower compared to fertility. So we had about 600,000 anomalous deaths in both directions. We also found that fertility changes tended to manifest over much longer periods of time compared to mortality, which is what we would expect. Mortality tended to be additive outliers, things that were happening in one-off, right? A hurricane, or September the 11th, or a tornado, that kind of or a flu outbreak. Fertility tended to have much more lingering effects. They tended to look like level shifts in temporary change, as opposed to just an additive outlier. But you can see we're looking at about 1.4% of the actual amount of mortality in the US was anomalous, and just under 1% of fertility in the US we detect as being anomalous. So not in the grand scheme of things, not very large, but they're very instructive on localized levels. Additive outliers were more common than temporary change and level shift. Here's the different types across the US and the number of anomalies within the historical time series. So in terms of mortality, additive outliers, you can see Texas has a large number of them, and so does Arkansas. In terms of fertility, additive outliers, there's very few. There's much more in terms of fertility, temporary change, and fertility level shift, where we find both New Hampshire, Connecticut, and New York experiencing some form of a fertility level shift. North Carolina exhibits a level shift in its mortality. Maybe somebody can figure out why. That's more familiar with North Carolina. This was in the mid 2000s that moves all the way up to the mid 2010s as well. And we detected no anomalies in Alaska, North Dakota, and South Dakota. Those are very small states, and so they tend to be more noisy, right? So it's harder, I guess, to fall outside of our significance area. And New York and Massachusetts had the most anomalies. They had 9 anomalies total between mortality and fertility. So they were the most anomalous states, which might tell us something about either the data collection processes on those states, or the fact that their demographic behaviors tend to be less predictable. So we think that this is still a very uncommon in social sciences, this type of approach. Typical hypothesis testing can be impractical using this kind of data, and you can just go ahead, because the numbers are so large, you end up with significant p-values almost all the time. Effect sizes can be very small, but you end up with these ridiculous p-values in a lot of cases, and you end up with a lot of p-hacking. This kind of doesn't allow as much p-hacking, or in some ways it does, where we just don't know what's driving it. Well, we think this is an appropriate approach for this kind of thing. There's all sorts of ways of implementing this. This is just one of them. Google has a tool called Causal Impact. Rob Hindman just published one on outlier analysis. Synthetic cohort and difference in difference are much more well known in here. But oftentimes you have to know the timing of the intervention for this. Over the summer, there was a paper got a lot of attention on the effect of Sturgis, the motorcycle rally, on COVID incidence and prevalence rates across the US. And they were using a synthetic cohort to do that, but they had to date it, right? They had to do a date from the beginning of the intervention. When does Sturgis actually begin? When does the effect actually begin? And depending on when you program that date in, could change the way that your analysis actually goes. What's really nice about this type of approach is you just plug it in, and it will actually tell you when the beginning actually occurs, when something is detectable in terms of a beginning. And of course, these modern statistical algorithms and in R become really easy to do. It's very flexible. Google's is really cool. It's got if you've ever used Causal Impact, it gives you a narrative summary so you can interpret what you're getting out of it. There's structural time series analysis as well that comes out of it. And I think that the ability to identify these different types of anomalies is really useful. It provides much better insight into long and short-term solutions to social problems, which, like, especially if we can link back some of these anomalies to actual policies that were put into place. If the outdoor smoking ban in New York actually contributed to a reduction in fertility, we can tell. And not only that, but when it actually began. And I hope that this type of work is a catalyst for curiosity, right? That we can actually begin to explore some of our data in ways that we didn't do before, because it's cool. It's really cool when you get your output and you're like, did you see that? What was that? What drove that? I was looking at stuff on Hurricane Maria after Puerto Rico and excess mortality, and I detect very clearly the mortality in Hurricane Maria and the lack of the federal response. But then just 5 years prior, I detect another significant mortality event in Puerto Rico that blew me away. I was like, what is this? What is driving this mortality change? Why is there excess I don't remember a hurricane hitting Puerto Rico 5 years before Hurricane Maria. It turned out there was a chikungunya outbreak in Puerto Rico that year that doesn't get a whole lot of play. So we can do this elsewhere. Well, I got some real quick next steps. Again, the algorithm is lightweight, it's flexible. This is mortality data from Spain, from the HMD, from the Human Mortality Database. Here, the T-scores are reported at the top. 1918, Spanish flu, massive mortality effect. The T-score here is 20, and it's an additive. We also detect, right, the Spanish Civil War beginning in 1937, and I'm assuming World War I in 1941 as well, where we get a big mortality event with the start of the war, 7.2. Here would be, again, this would be in Sweden. We get, look at that, 1918 pops up again. That's Spanish flu, the 1918 epidemic. But look at what happens historically. What happened in 1772 and 1773 in Sweden? 50,000 Swedes died that year. It was so huge. You can see the size of the mortality event on the spikes here. And then, of course, you can see the culling, right? The displacement of the mortality immediately afterwards. So why did this happen? Why did 50,000 Swedes die in the mid-1700s? Was it a famine that had happened? Was it some sort of an event? I don't know. I don't know. But we can turn all this data that we have and begin to look at different types of events, different policies that might have been implemented. Or we can cluster anomalies together across time. These are all the years for all the human mortality database countries, and how many years in the database had at least one mortality anomaly. So there were 9 mortality anomalies in the HMD for 1918. There's 13 candidate time series that had actual data in 1918. It's the Spanish flu, right? 1918 comes up. But what happened in 1866, where we have almost 40% of HMD countries have a mortality event? And again in 1877, what occurred in those years? Why have mortality anomalies largely ended? We see no common years in the HMD after 1952. Is data quality just so much better that we can't detect these? Or is modern society so much better at handling mortality events? And at least until 2020, where I imagine that we'll see a massive spike in the HMD going forward. So this is sort of an area where I'm starting to move through, and I'd gladly welcome any kind of questions that people have, or comments or suggestions as well.
Matt, thanks. That was really great. So there are 2 modes for asking questions. One is if you want to ask your question yourself, you can put your name in the chat and you will get unmuted and ask to pose your question yourself. And the other thing is to type questions into the Q&A. So I'm going to take the introducer's prerogative and ask a question right off the bat. One of the things that struck me as you were talking is that, for some of these events, you can look for corroborating evidence. So for like the dearth of births in, post-Katrina or around Katrina in New Orleans, presumably a lot of those were just displaced to other states. And so, I look at your data for that and I think, well, why isn't September an anomaly as well? Is it just below being one? And also, have you started to do stuff to look for just displacement? And particularly then when you want to think about policy impacts, if what you're seeing is a displacement of things rather than actual sort of changes in ultimate behavior, that's fundamentally, different and interesting.
Yeah. So the fundamental changes you can see, like in the Sweden example, that the time series is not linear in any way.
Right.
It's very non-linear. So any sort of underlying changes in behavior, generally the ARIMA model picks up on this very, very nicely, and it doesn't classify outliers. Maybe it could be argued that this increase in post-1950 Swedish mortality might be some sort of level shift, but given the history of this time series, it's not, right. It doesn't characterize it that way.
Mm-hmm.
So so I think that's good. On the downside is, yeah, some of these might be marginally significant, or they might be significant in terms of a traditional sense, right? Sort of, t-score of 2. But if we end up collecting what I would consider to be a lot of spurious effects. So in COVID, there's so many of these excess mortality ones that show, within 95% confidence of a given amount. And it's like every year there's a flu outbreak in December or January in these countries that trigger a significance, like they're above that 95% threshold. And it's like, well, it happens with a lot of regularity. Like it's really like it's a flu outbreak. Like it happens every year, and there's more mortality in that month, right? In the winter months. So the nice thing about using a much more strict definition is that we sort of weed some of these out, and we're really looking for the most significant ones. And they change depending upon your critical value. As you move it up, the ones that were marginal are now put back into the time series, and the model is re-estimated. So I haven't started looking at displacement for this. I haven't started looking at in that manner, or why some of the other ones don't pop up. Or even the other side, right, which is we should detect an anomaly.
Right.
Why don't we detect why isn't there one there, right?
Yeah.
Like, why is it that Connecticut has a fertility bust, but New York doesn't?
Right.
Like, why does that happen?
Yeah.
I don't, and so for this work right here, we're really not, we're not trying to actually look at all of those. We're hoping that this will actually spur as a catalyst for curiosity for people. Mm-hmm. So people with actual local knowledge or more domain specific knowledge for some of these would be able to pick them up and actually begin to look through. Like, we're hoping this is we're pointing arrows at some of this stuff so people can come back and actually and do more in-depth work there.
Okay, thanks. All right, we have tons of questions. I am gonna start with one from Q&A because those came in early. All right, a comment. What are some of the data sources you used for these demographic data? You mentioned the human mortality database. Are there any others?
Yeah, this works great with any kind of time series data, univariate time series data. You can use multivariate as well, but you don't have to. Oftentimes the controls that we might use don't follow the same way. It just doesn't, they're just not as correlated. But any time series data that you have can be used on this algorithm. I used NCHS for most of this. I used NCHS data, which is just CDC Wonder. But any data set that's a time series can apply. So in my sea level rise work, we use this exact algorithm to identify hurricane storm surges, and we're using tide gauge data.
Yeah. Cool. Tim, are you unmuting some folks?
Yes.
Great. Can you call on who's unmuted? Or am I supposed to?
So Barbara, Daniel, Alexandra, Jacqueline.
Okay, let's do Barbara, Daniel, Alexandra.
Okay. Hi, Matt. I really enjoyed your talk. So my question really is about a comparison with more traditional methods. Now, with traditional methods of analysis, not only do we have well understood tools for analysis, but we also have well understood tools for evaluating the quality of the analysis when we don't do it ourselves. And I'm curious, so with the methods you presented today, are there tools to evaluate the quality of that work that you presented, including the interpretation? I worry about people who have no social science or demographic background, just, going, having a romp through data and that somehow being presented as science.
Yeah, no, that's a really great concern. So like on this slide right here, Google's causal impact is one that actually provides a lot more. Well, you get model diagnostics that come out of all of these. It's just when I'm running it through essentially 102 time series, it's hard to present all of the model diagnostics at the end, right? So it's all included. That's the nice thing about many of these algorithms. And Chen and Liu developed it not specifically for this purpose. They really did it so you could correct for these and have an underlying trend. So if you had an anomaly, it wasn't pulling up some sort of analysis. So like a stock return or something like that. It's not really designed necessarily for this type of work, though that's like almost everything when it comes to tools. Google's
Right.
causal impact is pretty good with this too, and they developed it for trying to figure out the effect of marketing campaigns for their online ads, and you can use it for a number of different approaches. So like all tools, right? They can be kind of deployed in various ways. I guess some of them nefariously. And so hopefully we can all stick to Ipham's proclamation that we'll do things for good and never for evil. But yeah, I mean, being able to use these for non-experts for rolling these out, I mean, I guess I'm somewhat worried about it. Many people use synthetic cohort indifference and difference. They violate the assumptions in them. It's
right, but Matt, if I can interrupt here, the thing is that when they mess up, as a consumer of those analyses, I can often tell that they've messed up. How do I know as a consumer of this, not as a doer, but as a consumer, how do I evaluate the quality of the work?
Yeah, that's really hard. So I'll use the example of the ESA study with the Sturgis motorcycle rally that was like front page all over the place right in the middle of COVID. They were using a synthetic cohort method, and I couldn't replicate their results. When I actually dug it, because I mean the data is all public. When I dug it in, the only way that I could generate their results is if I assumed that there were no new infections in the United States, and that's the only way I could actually replicate their work. And yet they were using every modern bell and whistle for modern causal inference work. So I guess you can call, maybe it's more nefarious p hacking, right? Where you actually design your work, you plug it in so you get a specific result. So it's a worry I have about almost any technique, right? I mean, population projections, any kind of population analysis, any type of traditional demographic tool can be used, in the same kind of manner, can be kind of gamed. Yeah, I share the same worry. And I don't know, except for actually digging deep into the actual model output.
Right. Well, I'll let somebody else ask a question now, but this is my concern as a consumer. How do I evaluate it without somehow jumping in and trying to replicate it? But thanks. It's really interesting talk. I'll let somebody else ask questions. I don't want to dominate.
Okay, so let me see if Daniel Goodkin wants to ask his question, and then I'll read one that came in through the Q&A.
Okay, can you hear me?
Mm-hmm.
Okay, Matt, that was a really terrific presentation. I love your graphics. I have a question and a comment. The question is, do you really have to put this work under the big data umbrella? Because as you pointed out, time series approaches using monthly data have been around for quite a long time. And following up on Barbara's point, a caution here, in your introduction, you presented as a kind of exemplar of good causal inference, a study which implied that China's one-child program had a pronatal impact. So unless we can come up with some plausible explanation for how that could actually be the case, could that be more indicative of causal misinference?
So first with the big data, yeah, I mean, I guess it doesn't have to, right? But I mean, almost all demography is largely big data because we've had access to such large data sets for so long. And, big data kind of came up more recently, and it's kind of catchy in some ways. This is more like more like a data science kind of approach as opposed to big data. But I don't know. I guess I could change the title. I'm not really particularly wedded to it. As far as the example with the one child policy, I was just trying to find a good or a relatively quick example of using something like one of these types of approaches, difference in difference or synthetic cohort, at my fingertips to try and look at as an example of using these types of approaches in directly inside of demography. So in that case, yeah, maybe it would be, you know, misinference in those cases. And it goes back to what Barbara was suggesting about being cautious with these. And we should be that way in all of our work, right? That we should be very cautious about what our results say, because it can be so easy to get them wrong.
Right. Thanks. Good answers.
Okay, I'm going to read a question now that came in. So terrific work. Thank you. The questions are a couple questions. One, what was your process of identifying cause of anomalies for well-known events such as 9/11 and Katrina? Those may be a bit obvious and be explained by prior knowledge, but do the rest rely on Googling, reaching out to folks? What methods do you use to identify possible causes?
Yeah, so that's the nice thing about abductive reasoning, is that you're really looking for the most plausible solution, as opposed to, is this evidence or is this not evidence, right? It's not so cut and dry as we do with typical hypothesis testing. And so for some of these, it's sort of like, what's a good explanation for what we're looking at? What behind the driving force behind some of these anomalies? And some of them might be multi-causal. But we're not trying to pinpoint necessarily any one cause. So some of it is Googling, like Googling in the case of New York, you know, I was Googling, you know, what were major policies in New York that were put into place in 2004, and outdoor smoking ban came up right away. And it's like, well, that's plausible. I mean, it's related to mortality. It's about smoking. Maybe there was smoking cessation. That might be one, maybe it's not. Maybe people who know New York better would be able to explain it, and maybe it's spurious. I don't really know. So that's how we did it with things where we don't necessarily know the reason, or we would sort of, you know, reason through why. Like with Connecticut, we reasoned through. We were like, well, when was the stock market drop? And it's like 11 months earlier, and it's like, wow, you know, you got the stock market drop, you got 2 months for people to think about whether or not they might change their behavior. And then 11 months later, you have fewer kids. It seemed like it mapped on pretty clearly. And so some of these, Stephanie wanted to call up vital statistics offices and ask about some of the anomalies we detected. But for this paper, I didn't want to get stuck on that part, because I really wanted it to be about you know, hoping other people would have reasons, because I could reason something and be completely wrong with it. I could have a misinference. As Daniel said.
Okay, and then the second part of that question was, would something like increased mortality due to aging of baby boomers appear as an anomaly, or would the algorithm recognize the pattern and not see that as an anomaly?
Yeah, I don't think that the algorithm would find that as an anomaly. So the very long run level shifts, it has a bit of a hard time with. And you can see that in the case of Sweden, right? You can really see that here, that increase in mortality, more likely because of aging that's going on in the population, or even just general population change, might be what's behind it, and it doesn't detect it, which is good and bad, right? I mean, in some cases, it's good that we're not detecting something that might be spurious, but it's bad, and that maybe it would have been, right? We end up with a false negative in this case. But this is a multivariate approach, so you can add almost any other time series you can imagine, as long as it's in the same size, right? Everything it's still in the same time step. So if you had something else that might be correlated that you would think, you could throw it right in, and it would change all the estimates.
Okay, and then I think Shouting You has a question and is going to ask him or herself.
I'm just curious about the plots. It's really clear, so I would like to know how you generate these plots. Is that part of the package?
Yeah, it's native inside of the outliers package. In the paper, and I don't know if I do it for this one. It's just native out of it. For this one, this is ggplot. So it's doing, you know, some work after the fact. But yeah, it comes native within the package, which is really convenient. I've replicated the output, the plot style output in ggplot because in other cases because I like having multiples. But yeah, it's great. It's a really nice package.
Yeah. Do you have a reference? So like if I'm not familiar with this type of I did not use much, but it's very interesting. So if you have any good tutorial materials or references
For R or
for this packet.
oh yeah, there's a vignette for TS outliers. It's excellent for it. Yeah.
Okay, I just need to Google the name of the packet.
Mm-hmm.
It should pop up, right?
Yeah, and it also, you know, you can link right back to the 1993 publication too, which has a really great explanation.
Can you refer back the 1993 paper?
Yeah, it's Chen and Liu. Where's it at? Where's Chen and Liu? Where'd I put it? There it is. The Chen and Liu 1993 right here.
Oh, okay. Okay. Thank you.
They didn't make the package, but you know, there's another maintainer. But this is what it's based on.
Okay, that's great. Thank you.
Thank you.
All right, great. Well, we're at 1:02, and I know you have something 2 minutes ago with our trainees. So let me thank you again for this great talk and presentation. I know people really enjoyed it, and it was great to hear it. So thanks very much.
Thanks for having me.
You can imagine all the applause that's not coming through the muted microphones. Exactly. All right. Take care.
Thanks, everybody.
So much. Bye.